Hello again. So in this part, we are going to make an introduction to the natural language processing concept. This is an important title for us because natural language processing is one of the fundamental tools of data informatics. Data informatics is an area of its own. So because it's related to statistical analysis of different types of data and etc. However, most of the data we come across in real-world applications are some sorts of natural languages. It could be English language, related to linguistic, but it could be something else as well. For example, you could be analyzing some sort of code, C code, or a Python code. Python code is also a type of a language. And it could be data, because in data analytics, you're doing, for example, software management. And you want to do analysis on the codes written, then you would need tools from natural language processing. And recently, natural language processing and artificial intelligence, like 5 years ago, they've fused, they've become one. They are using the same tools and they are working on the same things, let me say, especially, which we do not cover in this course, the architecture, the so-called architecture transformers. Is one of the newest architectures, and it is both applicable to natural language processing and multimedia signal processing as well. So these two fields are becoming together. So what we can say is I've put some paragraphs from the Wikipedia about natural processing. It's a subfield of linguistics, computer science, and artificial intelligence concerned with interactions between computers and human language, like how to program computers to process and analyze large amounts of natural language data, whatever it is. Just like I said, it could be English language or it could be Python, whatever. The result of an NLP process is natural language processing module is a computer capable of understanding the contents of a language or a document or whatever it is. This technology can accurately extract information, especially in the recent years, and insights contained in documents, or maybe to categorize them, organize the documents for many purposes. So if you look at this diagram, you have programming, you have neuro techniques of artificial intelligence, and you have linguistics, and at the intersection point, it's NLP. So you have to know about artificial intelligence, you have to know about programming, and you have to know about linguistics. Good. So if you try to understand NLP, there are three main areas, guys. The very first journey of NLP started with early 50s. Actually, it's early 40s, because the famous Alan Turing's Enigma is type of a state machine that is trying to solve a type of a language. And starting with those years, with Alan Turing's Turing machine and etc., people have worked on understanding languages, modeling different types of languages, using finite state machines and symbolic mathematics. And this is called the symbolic NLP. It continued up to 90s. With 90s, so it's learning the semantics of a computational system. We're not interested in that. After 90s, with the increase in the computational capabilities of computers, mathematicians or NLP scientists started working on the so-called statistical methods. Today we know of the hidden Markov models and etc. Especially, this worked on until the last decade, early 2010s. And it ended with the start of neural NLP. So anybody who has done on NLP, who has done a PhD on NLP, or my age, my friends, they've worked on the statistical NLP, and I remember that. There was no neural NLP. However, recently, just like I said, the age of neural NLP becomes. So if you're interested, there's this provided some references for the historical versions. These are efficient, still computationally much efficient compared to neural NLP. So if you're interested, you can check. However, recently in 2010s, with the common usage of recurrent neural networks and LSTMs and further architectures just like transformers, the age of deep NLP or so-called neural NLP started. So this course is not about neural NLP, but I'm going to show you a gentle introduction of how NLP is related to the stuff we've learned and why NLP is a sequence modeling problem. So I'm going to start with, let me give you an advice. There's a very nice video, online course about this deep NLP. It is from Stanford, Professor Christopher Manning. So I strongly recommend you watch it if you're into the subject, because some of you, I know that, are into NLP. So this could be a nice point to start. So what is NLP? We simply treat a sort of language as a sequence. So for example, you want to do a machine translation. You feed a sequence, I am a student, and it says je suis étudiant, I don't read French. So that's the idea, to treat a language as a sequence. That's why we are interested, because we've been talking about sequence models and we've touched the borders of NLP because language is a sequence. How to model it? At this point, I'm going to talk about modeling words as a sequence. How to do it? Because word is just some text. But the models that I've seen up to now, like the RNN or LSTM, remember, they've accepted not words, they accepted some sort of vectors. So how to vectorize these words to a model to use? That's the first thing we should learn about NLP. And when you understand that, the interface of a language to a sequence model, you understand many things and you will be capable of experimenting with these models. Okay, so before that, let's try to understand what a word is in a language. Because the language, in its simple form, in English language, is composed of words. So in language, guys, we speak with some tokens, which we call words. They all have separate meanings. And when we construct a sentence, we use these tokens in a certain order. And more of the order with a certain relation of the tokens between themselves, so that the sentence we make sense. Okay? That's why the meaning of the word, the token, is very important for us. Because in the end, we are going to convert that token into a mathematical representation so that we can feed it to an LSTM. Okay? So in linguistics, previously, this is being studied. The meaning of a word, how to symbolize the meaning of a word, and etc. So NLP previously solved this problem by creating a large corpus of words, which was, for example, the famous WordNet. WordNet is a large dictionary of English words, which natural language processing guys used to relate different words to each other. So it's a set of lists, synonym lists, or hypernyms lists. So any relation you could find between these words, the tokens of that sequence, you could find there. So people, at the age of statistical NLP, used WordNet to model their tokens in a mathematical way, which represented these similarities defined in WordNet. Okay, how? I'm not going to get into the details, but this will bring us to somewhere. WordNet is a website called Princeton University. You can check it. It's a lexical database for English. There are lexical databases for other languages as well. But there's not our concept. We're going to get to the neural part quickly. It's good, but the problem with neural, statistical NLP was, although some words are synonyms, within the context of a sentence, being a synonym doesn't matter much. I mean, a nice example is provided in Manning's slides. For example, in WordNet, the word proficient is listed as a synonym for good. If someone does a favor to you, you say that, oh, you're a very good person. You never say, oh, you're a very proficient person. I mean, those kind of funny things happen when you're trying to speak a foreign language, but That's not the right way to speak the language. What I'm trying to say is, being a synonym is a relation. It can be used. However, the synonym relation is a handcrafted relation, which cannot be used solely to define the abstract relations between the tokens in a natural language. Because it's subjective, I mean, it's related to the context. If you don't know the context of the sentence, you cannot use it to model it. That's why in the age of neural NLP, people have found different ways to model these relationships. Again, following the age of neural NLP, they let the system learns these dependencies themselves. So instead of handcraftedly designing these relations between words, they've constructed models that can learn these relations. Okay. So how can we do it? So let's start working on this problem of representing words as vectors. The first solution is called the one-hot vectors. One-hot vector it is the simplest representation of a vocabulary, so-called vocabulary. Vocabulary is, you have a language, you have certain tokens in that language. In English language, tokens are called words. In Python language, tokens are called the expressions you use in that computer language. So there's a question on chat. Tık tık ses geliyor. Acaba nereden geliyor? İnşallah gelmesin de. Yani herhalde şundan geliyordu. Tamam, elimden geleni yapayım. Şekil değiştirdim. So what I was saying is, what we could do to convert these tokens into mathematical representations, right? So you have a vocabulary. In that vocabulary, you have tokens, words. Tokens are words. Words are tokens for English language. I want to represent them in a mathematical vector. Imagine I have a vocabulary of, for example, 20 words. I mean, I'm speaking a very simple language which has a total of 20 words. I can construct this one-hot vector where each token is represented by a 1 at a certain index and zeros for the other indices. For example, in this simple language model, vocabulary model, I have words motel and hotel represented this way. I mean, the number of dimensions in a language is more like 500,000. So this vector becomes 500,000 long. It doesn't matter, we are just doing a thought experiment. This could be a very simple way of mathematically representing it. There are nice things about this representation, guys. The nicest thing is, each word can be simply represented with a vector. However, the downside is, if you want to mathematically calculate a distance between these two vectors, so I'm calculating a distance, this is V1, this is V2. The distance between these two vectors could be, for example, the L2 norm. What is an L2 norm? You just calculate the differences of each element and get the square of it, which will be something like this, right? Because if you just 0, 0, 0, 0, 0, 1 plus 1, you're getting, so this is the sum of them. You're just summing these up. So there's no square root, I'm sorry. This is 2. The problem is, every token in this representation will have this equal distance of 2. Well, however, some words should have similar distance if we are modeling the context of these words in these vectors, right? I mean, motel and hotel are quite the same word. So their distance should be smaller compared to a mutual distance between the word motel and, I don't know, chair. Isn't that correct? So yes, these vectors are orthogonal, and the similarity of these vectors between any two words is the same. That's not something we want. We want a representation of the tokens where each vector will have a specific, where each token will have a specific vector. And the distance between those vectors will somehow correspond to the meaningful relations between the tokens of that language. That's the first problem you deal with in NLP, the word similarity. How to learn this? I mean, so when the thing I'm talking about is something that looks like this. So when you're feeding these, you can do this. By the way, you can do this. You can still do this. You can, for example, you want to construct a model, a neural network model. When it says something, for example, when it constructs, let's say we have an LSTM. You know what let's say an LSTM. Let me give you an example so that it will make more sense to you. You already learned about LSTM. So LSTM is something you feed an input and you get an output, so hidden state. So let me create a let me create a simple network here. So I have an LSTM, and I have another layer which is a fully connected layer. So let's not draw it that way. Let me draw it that way. Let me draw it that way. So this is X. This is the LSTM. And LSTM will output self states and hidden states for me. I create a fully connected layer. It's providing me a value. The output is 1, for example. So what I do is I'm writing words to it. So for example, let's say that this system checks if this sentence is grammatically correct. So it will output 1 or 0 to me. A value between 1 or 0. I don't know. It will output 1 or 0, theoretically. So what I do is I construct a sentence. I am Erdem sentence. What I do is I'm feeding each token one by one as a sequence to the LSTM, right? So I feed I will be represented as a one-hot vector. Sorry, I will be represented as a one-hot vector somewhere, like 1. I feed it. The LSTM hidden states change. It creates a fully connected layer, creates output. Then I feed M, another type of vector. I feed this. LSTM works on its hidden state. The hidden states change. The hidden states will create another value out of the fully connected layer. I feed Erdem, and I feed the dot. And the final value of the fully connected layer, either it's becoming 0 or 1, telling me that if this is a grammatically correct sentence or not. So with this model, I can simply create models that I can train with. Nothing stopping me. Okay, so you can do this. In this case, your LSTM will try to learn the similarities itself, because with this one-hot vector model, you are feeding the words as a similar distance to each other. Every word is the same for you. And the relations between the words would be learned by the LSTM. But to make the LSTM's business easier, you could try something else. Imagine we had a simple way, to convert any word to a not one-hot representation, but these numbers. In that case, we would be calling them the word embeddings. Actually, in your first lab, your teaching assistant Ozan tried to explain this, and it was a bit confusing, but this is the story. The way you convert a token into a vector that you could feed to a model. But how to obtain this? I mean, so before we get how to obtain this, what would this mean to us? For example, you have all the words of the English language. You have converted them to a vector of length 9, right? This is 9, right? 8, sorry, vector of length 8. So you are representing each word with real values in an 8-dimensional space. 8-dimensional space. So this is 8 by 1, right? 8-dimensional space. So in this case, unlike the one-hot representation, each word will have different distances between them, and depending on their values. How did we obtain these values? Let's not think about it. Somehow we are given those values. For a proper modeling of the language, what we need is the distances of these words will somehow represent the context and the meaningful similarities of those words as well. So this vector is an 8-dimensional vector. It is hard to depict or visualize the relations between the words in an 8-dimensional space. So what I'm going to do is imagine this 8-dimensional space, the similarities between it, the distances between this 8-dimensional space is somehow projected into a 2-dimensional space. In that case, I would expect the vocabulary and the word embedding to create distances where, for example, the word come and go will have vectors which has smaller distance. The words need and help having distance smaller to each other. The word say, think, expect, it's smaller distances. Are, is, were, was, smaller distances because they are of kind of the same category. Or had, has, have, similar. Are and has and being kind of closer to each other, but come and go distant from them. So this is a 2D projection of an 8-dimensional similarity space, so it is difficult to visualize, but that is what I would expect for an embedding to do. This is very important, guys. This is the first step of NLP or any type of language-based sequence modeling. You convert your tokens to this representation. And there are ways to do it. A simple way is called the linear embedding. And you can do this in Python. Actually, most probably your TA is going to show this in your labs. For example, you have a vocabulary, you have this word, I am Erdem, dot being the fourth token. So this is token 1, this is token 2, token 3, token 4. That is important because it is an indication of the end of the sentence. So you have a vocabulary of, for example, n. You can create, what you can create is n length one-hot vectors in your space. These are all n by 1. So one-hot vectors. And this dot being the last one, I don't know. You can create this is n, but you want to represent them in an 8-dimensional space. What you can do is, you can create a linear layer where your one-hot vector, for example, 1 is somewhere 1, of n in a fully connected linear, so linear layers are called fully connected layers, where the weight is n by 8, will create values of 8. So this is the vector. So there's a weight matrix here, which is n by 8 by n. So what you do is weight 8 by n times this t1 vector, which is n by 1, will create a vector for you, which is the vector 8 by 1, right? So a linear layer would do this for you. How to find the weights of this linear layer? Well, put it in your graph in PyTorch and let it be trained during the training. So this embedding layer can be trained and learned. And that's what you usually do in these NLP problems, okay? But in NLP literature, there are different ways, which are beyond the scope of this course, but I will mention. In NLP,
can I ask a question?
Please, I'm listening to you.
If we have a two-long passage, converting one-hot vector can create sparsity, and
yes.
How can we handle this? And why we change the dimension 8? Is it it has a special meaning behind it.
So you're asking two questions. Let me understand the questions one by one. We're asking what would create sparsity when we are doing the embedding? What would exactly create the sparsity in the embedding? Can you repeat that again?
If we have too long passage, we have many words, and
if we have many words in the vocabulary, yes.
Yes. And if we encode them one hot vector,
yes,
it may create
sparsity. Definitely, it's what your friend is saying is. Imagine I have 500,000 words in my vocabulary. If I represent them in one hot vector representation, most of the vectors will be very sparse, full of zeros. That's something that we don't want. And what is the question?
And how can, why we change them in 8 dimensions, please?
Well, okay. The obvious answer is the thing that you're asking, to get rid of the sparsity. Because not exactly, it doesn't have to be 8, but it's a hyperparameter to choose. So it's going to be much less than the actual vocabulary size, so that we get rid of the sparsity. There was a second question, yes?
Yes, one last question. When you mentioned linear encoding, what will we put the ground truth for the training part?
Whatever your problem is, let's get back to the problem that I was studying. So your friend is asking, I'm going to create the linear embedding. How am I going to create the linear embedding? Actually, the answer is, you're not going to create the linear embedding as a separate part of your problem. It will be part of your network. So let me get to the network where we test the grammatical correctness of a sentence. Remember that, the previous one? So I'm putting a linear embedding layer here, then an LSTM, then a fully connected layer with 1. So this is zeros and ones. I'm feeding different words to here. I am Erdem, am I Erdem, I Erdem, I am, kind of. Some of them are correct. I feed ground truths 1. Some of them are incorrect. So I trained all these layers together. A linear encoding layer is just some weight multiplication between the 1-hot vectors and to the, for example, 8 long vectors, the embeddings. So during backpropagation, for this problem, these embeddings will be learned. So don't think of the embedding as a generalized form of the language. Actually, word-to-vec is, which I'm going to be showing in the slides after this question. But the linear embedding you learn will be a specific type of embedding, which will be useful for only your problem that you have trained your system for. Answer to your question?
Thank you.
Okay, okay. Okay, your friend is asking, how come I create the weights? The weights creating for the linear embedding is a part of your network. They are going to be created as a part of the training itself. So it's just a layer. And the type of linear embedding you will create for this simple problem will be different than another problem where you have a different set of architecture and different set of problem and different set of ground truth. Okay. So this was a very good question in the sense that we realize the embedding we use for these tokens does not necessarily have to be unique. For different purposes, we may have different types of embeddings. And we may not understand them necessarily. They don't have to be transparent. I resemble this embedding into a feature extraction step. Remember, when we talked about convolutional neural networks, convolutional layers replaced the good old pattern recognition handcrafted features we said. And actually these embedding layers that learn themselves from the data are like the deep learning version of the NLP for feature extraction. And actually that was what Ozan was trying to say when he talked about these embedding layers in your first lab that confused you. Because you were not ready to learn it yet. Now you're ready. Okay. However, having said that, having talked about a general form of an embedding for language representation, there is one idea, which is Mikolov's 10-year-old word-to-vec. This is still a data-based approach, which is to create an embedding method for a given set of data. So for a given set of data, you used word-to-vec algorithm to create an embedding method. But unlike the one that I've mentioned in that simple architecture, instead of finding an embedding specific for that problem definition, because that embedding will only care about solving that problem, grammatical correctness problem, if you do it that way. Word-to-vec is a more general embedding, which is obtained from the corpus itself, not any problem definition. So for word-to-vec, you don't need a ground truth. You only need proper sentences. So that's kind of a different approach, let me say. It's more like the statistical NLP age approaches. And what you have is, you have lots of valid sentences from a language, I mean, tens of thousands of. And what you obtain is a vector for each word. Word-to-vec algorithm is beyond the scope of this course for two reasons. Because we are not an NLP course. The second reason is we are not interested in this non-neural techniques. We are a deep learning course and we are interested in the neural network techniques. That's why the linear layer that I mentioned is more relevant to us. Okay, but if you're interested, I've provided some blogs and stuff in the last slide. Okay, and just to conclude, there are two very well-known methods for word-to-vec, skipgram and continuous back of words, which kind of checks the corpus and the words' relation to their neighbors or their frequencies in the sentences and decides on a vector value. Okay, they have different strategies and different strategies work better for different NLP problems. But remember, we are deep learning people, and in the end, it is best that we work on a layered model for embedding so that we could learn a specific embedding which is specific for our problem. Just like convolutional neural networks where we obtain the specific features which is specific for our supervised problem. However, there are unsupervised problems and there are many problems that you need to work with word-to-vec as well. But this is beyond the scope of this course. Okay, so the output of the word-to-vec is the vectors we use to present the words called neural network embeddings, but you could use them, you could use a linear embedding vector to learn them as well. So word-to-vec vectorizes the words, nothing else. It's an encoding, just like a feature extractor. Okay, there are many word-to-vec implementations already you can find in the internet, and people use them because they are pre-trained, ready-to-use interfaces. For example, for the Python language, people are working on NLP applications of Python language. For example, if there's a malicious code inside a large corpus of code, they first transfer the code into a vector representation using a pre-trained word-to-vec, and they train their LST or LSTM or sequence model because the code language is a sequence. It's varying length and it's a bunch of tokens which are attached in front one after another. Okay. Okay, so I'm going to give a break right now, and before I finish, I'm going to talk about the encoder-decoder models of sequence-to-sequence modeling, which will be another gentle introduction to the subject. Any questions before the break? Okay, past 40 then, past 40.